So the final talk of this session is going to be by Shivam and Vats, and it's on learning to avoid local minima and planning for static environments.
Hi, so I'm Shivam. I'm an undergraduate student at the Indian Institute of Technology, Kharagpur. This is joined to work with Venkatraman, Narayanan, and Professor Maxim Likhachev here at CMU. So we'll be talking about the problem of motion planning using heuristic-search algorithms. And I want to give you a sense of what the problem is before we start. So we have a robot before us, and we have a known environment, and we want to plan a path from a start configuration to any given goal configuration. So for example, if you're planning in this hall, we might want our robot to go from this state in the hall to any other end of the hall, right? So to be able to do that, you need to find a plan which satisfies the constraints of the robot and is collision-free. That's essentially the problem of motion planning. So here we have a manipulator called the PR2, and it has different joints in its hands. It can move around, and every possible configuration of those hands and locations essentially corresponds to a location in your search space. So we define our search graph as in an implicit fashion in terms of a successor function, which returns the successor of every node. In this case, each vertex corresponds to each state that the robot can be in the search space, and an edge essentially is a transition from one state to the other. So for example, these are small motions. These could be arm motions, the base motions, and so on and so forth. And that's how we build our graph for our search. Now, in many motion planning domains, especially for applications, we see that the environment is largely static. So for example, if you consider this room, apart from the people, most of the major features are static. For example, in warehouses, most of the shelves are static. So the question that we consider is that if we have this information that the environment is largely static, can we in some way use some offline pre-processing to speed up our search? And there has, of course, been some work in this area. The closest that comes to our work is Marvin, which learns plateauscaping macro actions. Our work is different from this in the sense that we add new edges to our search graph rather than these edges being compositions of existing edges of the search graph. Similarly, we have experience graphs which creates a heuristic which biases the search towards previously generated paths. Now, when you're using heuristic search, the crucial factor which decides the efficiency of your search is the presence of local minimum. And these are essentially regions where the heuristic is weakly related to the cost to goal. So for example, if you're using a Euclidean heuristic in this case, you might have to expand all those states to finally figure out that you needed to go the other way. Now, the state which you finally discovered after expanding all those useless nodes is what we call an exit state, because it helped you come out of a local minimum. And what we claim is that, especially in high-dimensional spaces, when you are doing manipulation, there are lots of these local minimum. And if you can identify these local minimum beforehand and learn how to avoid them, you can speed up the search. So our first contribution is we propose a method to identify these local minimum given an environment. And second, we propose a technique which makes use of this information to speed up any heuristic search algorithm. The algorithm has two phases. The first is a learning phase, and the second is a planning phase. In the learning phase, you figure out where these local minima are, and in the planning phase, you make use of that information for future search queries. So, for example, if you consider this kitchen-like environment, where do you think the local minima might be? So, for example, if you are using a base heuristic, which essentially tells you that what the distance of your base is from the goal, and you are using a mobile manipulator like I showed you earlier, well, you might guess that the robot might get stuck in the door because, well, it has an arm and it doesn't really know which way the arm should be oriented. It might also get stuck near the tables because, well, it cannot really reason about which way to go and does not know whether it will fit between the tables or not. So we would like to identify the major local minima in this environment. And the basic intuition is that the amount of time you spend in coming out of a local minimum is directly related to the size of the local minimum. So for example, if you look at the time spent in doing a search, and if you look at these states which took the maximum time to be discovered, that will usually correspond to the size of the local minimum. So firstly, of course, we want to get an idea of the environment. We want to get a model of the environment in terms of the local minimum. So we randomly select start and goal pairs from the environment, and then we plan between those start and goal pairs. During search, we put a timestamp on each of these nodes whenever they were expanded. Once the search gets over, we look at the states which finally made it on the final path. So for example, if you expanded 1,000 states to find a solution, and only 100 of them finally made it to the solution, you will look at those 100 states which are on the solution. Now we calculate the first difference of the timestamps. This essentially means you are trying to find out how much time a particular state took to be discovered after discovering the previous state on the solution. So the graph usually looks like this. A peak usually means that that particular state took much larger time to be discovered than both the preceding and the succeeding state. So our basic claim is that these peaks are representative of the local minima in the environment, essentially because these states are taking disproportionate amount of time to be discovered, and we want to avoid these local minima so that we can speed up the search. Now, if you look, this is the top view of a door in the environment that I showed you, and that is a robot, the PR2, with its arms out, with its arm outstretched. Now, if you think about it, the robot cannot get through the door in any other configuration. For example, if you are using a base heuristic which tells it the distance between its base to the goal base state, it cannot reason about the right arm configuration, right? But so when the robot gets near the door, it will probably expand a lot of states to figure out that, well, this is the right state which helps it get through the door. Now, we would like to identify states like these and help the robot directly go to this state without doing the wasteful expansion each and every time. We model this information in terms of an activation region. It essentially is a hypersphere which approximates the local minimum. So the exit state that we talked about essentially corresponds to the center of this hypersphere, and the radius is some approximation of the size of the local minimum. Now, when we are planning, the basic strategy is the following. When you feel that you are likely to get stuck in a local minimum, you try to move to the exit state of that local minimum before you get stuck. So for example, if you're near the door and you know from your prior experience that, well, previous searchers had a hard time to go through the door, you remember the exit state, that is the correct configuration. So when you're near the door, you try to move directly to the exit state or the right arm configuration which took you through the door in the previous searches. In terms of the activation region, you check whether or not you are inside the activation region, and then you add an edge to the exit state. So, for example, if you look at this small graph, the shaded region is the local minimum, and that's your exit state which you have learned in your learning phase. Your current state is here, and you're trying to go to the goal to the right. Now, when you reach the end of the local minimum and you check your distance from the exit state, you realize from an experience that it is likely that you might get stuck again in a local minimum. The previous time you had to expand all those states to make it to the exit state because, well, your heuristic is not really helping you. But in this case, since you know that the right state which you should be in to get through the local minimum, you add a new edge to the exit state. So here we are modifying the search graph. We are not using the edges of the search graph, but we are adding a new edge. You can do this in terms of a local planner. It could be as simple as by interpolating. So for example, interpolating could work in the continuous domain. Now, right, so once you have this new edge, you simply add this state as a successor to the current state. So the search can choose whether or not it wants to jump to the exit state. So in this way, it guarantees the optimality bounds because you're not forcing the search to take any particular path. You're simply giving it an option to move to the exit state if the heuristic cost is, well, useful. Now, we did experiments using this approach in the 11 degrees of freedom mobile manipulation domain. And essentially, the search space has 11 degrees of freedom, 6 for the end effector, that is the end effector of the robot, 3 degrees of freedom for the base, x, y, z, and we have the spine and another free angle. And so we did this using a multi-heuristic A-star framework, which essentially means that you're allowed to use multiple heuristic. This works well in this domain, so that's why we choose this. And the heuristics that we essentially used was base heuristics and end effector heuristics, which is what is the distance of your base to the goal configuration and the end effector configuration. we use the kitchen-like domain, which is very similar to indoor environments that we usually see. And the planning problem is to start from a given configuration and reach an end effector configuration. We randomize the environment by adding more obstacles, and we then averaged out the results. So on an average, we get a speed up of around 1.5 to 2.5. These are different variations of the same algorithm, but the speed up is almost similar, which means that it is generalizing across different variations of the algorithm and is not really algorithm dependent. So in future, we would like to detect better models of the local minimum. So currently, we are modeling it in terms of a hypersphere, which is rather a simplistic model. We would also like to generalize it across different environments. So for example, if you know how to get through one door, you should be able to reason how to get through other similar doors. So for example, in the current formulation, if you move the door to someplace else, well, that information is not really useful. So that's one really interesting future work that we would like to look into. To summarize, we looked into the problem of how heuristic search is affected by the presence of local minima. The key idea was that these local minima can be identified in an offline planning phase. And then we proposed an algorithm which has two phases. In the first phase, it learns these local minima in an offline fashion. And in the second, given a new search query, you modify the search graph to avoid getting stuck in those local minima. And finally, we showed by experiments how these can be used in high-dimensional search spaces, for example, in mobile manipulation. Thank you.
So we have time for some questions.
During the experimental phase, you changed the environment, right?
Yeah.
Different runs.
Mm-hmm.
I was wondering, do you have to rerun the learning phase on every new environment, or do you exploit the previous information to better perform when the environment is changed?
Yeah, so that's a good question. So currently, when you change the environment in any major fashion, so for example, if you move the tables, if you move the door, you need to rerun the experiments because, well, the local minima have now moved. So currently, this is not generalizing across major changes in the environment. But that's something we would like to consider in future work.
Okay, good question. So yeah, very interesting way of defining local minima. So when you get a local minima, you were somehow adding this blue arc. Mm-hmm. And was that an actual path that the system could actually take?
Yeah, so that's actually, so for example, in robotics domain, the space is continuous, right? So you can use any local planner to find another path.
Presumably you already had a path because you planned for it once.
Yes.
Just add that in, or was it?
No, so it's a totally new edge. You don't learn the whole path. So for example, if you try to explore, if you get inside the local minimum and then you're again trying to find a path, well, that's again using the wasteful expansions, right? So here you are just remembering the exit state, which helped you come out of the local minimum. And then you make use of a different local planner, which is capable of giving you an extra edge from your current state to the exit state.
And could you have just sort of cached the original path that you had, or not?
Well, you could, but then of course, we are only learning the exit state and not the start state, right? So the path will depend on where you start from, right? So
yeah,
then you'll have to learn every possible start configurations, which is not really feasible.
Sure. Yes.
I know your points are in 6 dimensions, but when you project them back into 3, where do these local minimum points show up on your
Well, these might show up in like the full dimension as well. Yeah.
Oh no, but I'm just curious.
Uh-huh.
Like, is there geometric intuition about
Yeah. So for example, so for example, if you look at this door, right? So if you're using a base heuristic, which essentially just calculates the distance between your base and the goal base, you have no idea which way to orient the arm, right? So for example, physically, there will be a local minimum near the door. So for example, if you're approaching the door from that side, from the top, and you want to go to the other side, and you reach somewhat near the door, you would want to directly go to this particular state rather than expand and then figure out that this is the best possible state, right? So physically, you would assume that wherever the search takes a lot of time to find a path, that will correspond to a local minimum.
So it's going to be features such as doors or corners or...
Well, it could be. So it depends on the interaction between the obstacles, right? So for example, if the door had been much wider, for example, let's say, wider than the robot itself, then it wouldn't be a local minimum because it doesn't really matter which orientation the robot is in. Yep.
One more question and we'll get coffee. Yes.
Is your approach just any kind of topological cases, like you add new edges to the search graph, then maybe there could be a continuously infinite number of exit states, and you can add too many local search edges to your search. Does that happen? Something like that?
So, well, you could possibly do that. I mean, so like I said, the way we are modeling the local minimum is rather simple, right? So we are just modeling it in terms of a hypersphere, whereas the local minimum could be of much more complicated shape. Similarly, there could be multiple ways via which you can come out of the local minimum. So currently we are not biasing our learning algorithm to go for a particular local minimum. So we are just randomly trying to plan and find out the local minima, right? So we have essentially just 1 or 2 exit states per local minimum. So that's not something we are controlling right now. So, but yeah, there could be possibly multiple ways to come out of the local minimum.
Okay, thank you.
All right, well, let's thank the speaker.
Thank you.